Pluto's trajectory has always been expected to raise concerns. Its orbit crosses paths with that of another planet. Pluto, the small and enigmatic planet situated in the outermost reaches of our solar system, has become a focal point in astronomical discussions. Recent developments have sparked concerns about a possible collision with Neptune, which has alarmed both scientists and space enthusiasts. Notable figures, such as Neil deGrasse Tyson and Michio Kaku, have voiced their worries regarding the possible consequences of this cosmic encounter. But what led Pluto onto this potential collision path with Neptune, and what could this cosmic clash mean for Earth? Join us as we delve into how this massive event might have occurred and why scientists are concerned about this celestial anomaly. Once hailed as a full-fledged planet, Pluto underwent a significant reclassification, now classified as a dwarf planet, primarily due to its erratic orbit. Despite this redefinition, Pluto continues to intrigue and spark curiosity within the astronomy community. Recently, prominent scientists like Neil deGrasse Tyson and Michio Kaku have raised alarms about Pluto's path potentially crossing Neptune's, suggesting a risk of collision that could have profound consequences for our planet. Pluto's journey around the Sun is remarkable due to its unique properties. Its orbit is exceptionally long, taking an astonishing 248 years to complete a single revolution. Since its discovery in 1930, Pluto has not yet finished one full orbit around the Sun. What makes Pluto even more fascinating is the highly elliptical shape of its orbit, which contrasts sharply with the near-circular orbits of the other major planets. Furthermore, Pluto's orbit is tilted at a 17 degrees angle relative to the ecliptic plane, resulting in a steeper incline compared to the orbits of other planets. This combination of inclination and elongated orbit adds complexity to Pluto's motion. A notable feature of Pluto's orbit is that it intersects Neptune's orbit every 20 years, bringing Pluto closer to the Sun than Neptune. This challenges the typical expectations of their relative positions within the solar system. Further analysis reveals that Pluto's orbit is far from circular, instead following an elliptical or oval path. This means its distance from the Sun varies greatly throughout its orbit. At its closest approach, Pluto is roughly 30 astronomical units from the Sun, while at its farthest point, it extends to over 49 astronomical units, nearly double the distance between Neptune and the Sun. Moreover, Pluto's orbit is tilted in relation to the orbits of other planets, adding another layer of complexity to its interaction with Neptune. This tilt plays a crucial role in how Pluto and Neptune interact when their orbits overlap. Their gravitational forces tug at one another, gradually altering their trajectories. This interaction highlights the interconnected nature of our solar system, where each planet exerts gravitational forces that influence the movements of the others. In recent years, technological advances in observational tools have enabled astronomers to track Pluto's movements with greater accuracy. This has enhanced our understanding of its orbit and the potential impacts it may have on the stability of the outer solar system. While the chances of a direct collision between Pluto and Neptune remain minimal, the possibility is still under examination. Ongoing monitoring continues, as any collision could lead to significant consequences. Despite its small size and remote location, Pluto remains a captivating subject of study for both scientists and space enthusiasts. A critical question that arises is why Pluto has not yet collided with Neptune. The answer lies in the gravitational influence of other planets. Since Pluto's discovery, astronomers have been attempting to understand its path. Unlike most planets that maintain a consistent orbit within the ecliptic plane, Pluto's orbit stands out due to its steep tilt and elliptical shape. The mystery deepened when it became evident that Pluto's orbit crosses Neptune's, yet despite the apparent danger, Pluto's orbit remains surprisingly stable. This stability suggests the presence of complex mechanics that govern space dynamics. The study of Pluto's interaction with Neptune and the Sun presents significant challenges for astronomers. Predicting the movement of celestial bodies involves a thorough understanding of how their gravitational fields influence one another. To navigate this challenge, scientists use specific terms, such as ASMU libration, latitude libration, and VSOP, von Zeipel, Steves, and Kaplan isolation, to solve this cosmic puzzle. ASMU libration, for instance, helps maintain the stability of planetary orbits. When Pluto crosses Neptune's path, it remains at least 90 degrees away, preventing a direct collision. Latitude libration ensures that Pluto remains above Neptune's path during close encounters, further reducing the likelihood of a collision. The VSOP oscillation, named after scientists von Zeipel, Steves, and Kaplan, explains why Pluto's orbit appears unusual yet remains stable over time. Despite the apparent chaos of space, underlying patterns exist that help maintain order. These patterns prevent Pluto from colliding with Neptune or undergoing drastic changes in its orbit. Orbital chaos, a phenomenon that describes how the trajectory of a celestial body is sensitive to its initial conditions, is vividly demonstrated by Pluto's orbit. Even slight variations in Pluto's position or speed can lead to significant changes over long periods. Scientists use advanced computer simulations to model Pluto's interactions with other celestial bodies, like Neptune, and to investigate the effects of small changes in its trajectory. In the late 1980s, these simulations revealed something fascinating. Despite Pluto's orbit's apparent stability, it can still behave unpredictably. A tiny change in Pluto's starting point or speed could dramatically alter its orbit over time. However, even with these uncertainties, Pluto's orbit is expected to remain stable for billions of years, suggesting that despite its erratic appearance, there is an underlying order to its movement. The unpredictability of planetary orbits like Pluto's makes it difficult to predict long-term changes with certainty. These models require extremely precise initial conditions, as even small errors can lead to vastly different results. This makes accurate predictions about Pluto's future trajectory incredibly challenging. Understanding Pluto's orbit is vital, particularly when considering the possibility of a future collision with Neptune. This knowledge contributes to our broader understanding of how our solar system functions. Pluto's orbit serves as an example of how seemingly chaotic paths can eventually reach a stable equilibrium, guided by gravitational forces and motion. It is essential to continue observing and studying these celestial mechanics to gain a deeper understanding of our place in the universe. Pluto's orbit offers an excellent illustration of space's unpredictable nature. Its elliptical orbit, leading to occasional close encounters with Neptune, makes predicting the system's long-term dynamics extremely challenging. However, gravitational forces play an essential role in preventing Pluto and Neptune from colliding. Gravity, the force that attracts objects to one another, ensures that despite their intersecting orbits, Pluto and Neptune remain apart most of the time. These gravitational interactions illustrate the delicate balance of forces at play in space. While the likelihood of a collision remains remote, it would be a monumental event with dramatic consequences. Such an event would fundamentally alter our understanding of the solar system. Although space exploration has made great strides, Pluto's orbit serves as a reminder of the many mysteries that still remain unsolved. Scientists continue to study Pluto's path to better understand how the movements of large planets influence smaller ones. This knowledge is essential for understanding the intricate relationships between celestial bodies and how their movements can affect one another. Despite Pluto's unusual orbit, renowned scientists such as Neil deGrasse Tyson have speculated that a collision with Neptune might one day happen. Tyson, a leading astrophysicist, views Pluto's reclassification as a dwarf planet as a necessary step, acknowledging the importance of continued exploration and study. He believes that Pluto's strange orbit highlights the fact that much remains to be learned about space and the forces governing it. Tyson emphasizes that the mysteries of space are what make studying it so captivating and encourages others to engage with the complexities of celestial mechanics. Tyson and other experts remain concerned about the potential dangers of Pluto's unusual path. Should a collision between Pluto and Neptune occur, it could have catastrophic consequences for our solar system. The release of energy from such an event would be immense, and the debris scattered throughout space could have widespread effects, possibly even impacting other planets and moons. Neptune itself would likely be affected, with its orbit potentially altered, further complicating the dynamics of the outer solar system. Renowned theoretical physicist Michio Kaku, known for his work in string theory, also offers valuable insights into space exploration. Kaku believes that studying phenomena like Pluto's orbit is crucial for understanding the broader principles of celestial mechanics and theoretical physics. He suggests that examining Pluto's interactions with Neptune can assist scientists in ensuring the safety of future space missions. Kaku also underscores the importance of understanding gravitational forces within the context of space exploration, as they are fundamental to shaping how we approach distant worlds. Kaku's research in string theory, which seeks to explain the fundamental forces of the universe, aligns with his interest in Pluto's orbit. A collision between Pluto and Neptune could provide valuable data, contributing to our understanding of gravity and spacetime, core elements of string theory. While such an event would have minimal direct impact on Earth, it could present a unique opportunity to study the behavior of fundamental forces in extreme conditions. As scientists continue to probe the depths of space, the unpredictability of planetary interactions becomes increasingly apparent. Studying celestial dynamics, such as the intricate gravitational relationship between Pluto and Neptune, provides valuable insights into the fundamental laws governing the universe. By continuing to monitor and study these phenomena, we move closer to understanding the vast and complex nature of the cosmos. The gravitational interactions between Pluto and Neptune demonstrate how even distant planets can influence one another. These celestial bodies exert gravitational forces that, over time, can subtly but significantly shape their orbits. While a direct collision remains unlikely, it is not entirely outside the realm of possibility, leading to ongoing interest and observation from the scientific community. Researchers believe that understanding these forces may one day enable them to predict and mitigate the risks posed by such cosmic events. One intriguing aspect of planetary motion is how seemingly chaotic or random interactions can ultimately result in stable, predictable patterns. This is particularly true for Pluto, whose orbit may seem erratic but is governed by precise gravitational forces. These forces help prevent Pluto from colliding with Neptune, despite their overlapping orbits. The delicate balance between the gravitational pull of other planets and Pluto's orbit ensures the dwarf planet stays on a steady, though intricate, course. Understanding this intricate relationship is essential for advancing our knowledge of the broader solar system. As scientists continue to study Pluto's unique orbital characteristics, they also look to other areas of space exploration. For example, studying systems like TRAPPIST-1, which contains multiple Earth-sized planets, helps astronomers learn how gravitational forces between planets can lead to orbital resonances and, in some cases, increase the likelihood of a planet's orbit becoming unstable. Although the TRAPPIST-1 system is not currently facing any collisions, scientists remain vigilant, tracking the movements of planets in these crowded environments to better understand the risks and how they might evolve over time. Meanwhile, astronomers are also focused on understanding the behavior of rogue planets, planets that drift through space without being bound to a star. These rogue planets, which wander aimlessly through the vastness of space, offer an intriguing aspect of study, particularly in understanding the formation and evolution of planetary systems. While they may not follow predictable paths like planets bound to stars, their movements and gravitational interactions with other celestial objects can have far-reaching effects on the dynamics of the space they inhabit. The behavior of these rogue planets may also provide important insights into the future of our own solar system, as the possibility of an interstellar object passing through our solar system could lead to unexpected gravitational influences.